Today we have the topic, about the colligative properties in our chemistry. So one of the most important topic is colligative properties. This colligative properties is related to our solution. As we know, the solution is the homogeneous mixture of the solute and the solvent. Right? In our previous class, we discussed about some important properties of this solution. So even in our last class, what we discussed about types of this solution, ideal solution and non-ideal solution. Here we have a very important topic, that is the colligative properties. So colligative properties, the properties of our solution, right? So before we discuss more detail about these colligative properties, so let me highlight some important properties of the liquid. One of the very important properties of the liquid is the vapour pressure. So vapour pressure is the one of the most important properties of the liquids. This property is playing a very important role to the other properties of our liquids. So I think you remember what do you mean by vapour pressure. So let me just shortly explain to you what do you mean by vapour pressure. Vapour pressure, as you know, is the properties of the liquid. What type of the properties of this liquid is the escaping tendency of a liquid into the vapour phase. Some of the liquids are having the high escaping tendency into the vapour phase. So that types of the liquid we can consider as the high vapour pressure liquid. And some liquids having the low escaping tendency, very low escaping tendency, like the water, right? So that types of the liquid we consider as the low vapour pressure, right? So now this vapour pressure, what are important factors affecting on this vapour pressure here? So one of the important factors, as you know, that is the nature of the liquid. Some liquids, different liquids have a different vapour pressure, like the water. When we compare with the ethyl alcohol, as you know, ethyl alcohol is the high vapour pressure compared to the water, right? So and the petrol, as you know, the petrol is a very high vapour pressure, right, compared to the water. So now here, so then another factor is the temperature. So when the temperature increase, the vapour pressure of the liquid increase. That means, so it can be easily vaporized. That means the escaping tendency should be very high. Then what the another important factor is the amount of solute adds, right? So in our liquid, when we add some amount of the solute, right? So what would be the effect of vapour pressure? As we know, so when we add some amount of the solute, that solute molecule occupy the surface of that means outer surface of the liquid. So when the outer surface of the liquid is occupied by the solute molecules, so the vapour pressure of our liquid or solution becoming the reduced or lowering, right? That means, the vapour pressure of the solution is lower on addition of the some amount of the solutes into the solution, into the liquid, I should say. That means, right? That is, the vapour pressure of the liquid or solution is lower on addition of some amount of solute, right? Don't forget, that's the very important. So how I write lowering of vapour pressure. So as we know that, the vapour pressure of the solution, I write vapour pressure of the solution. Vapour pressure of the solution, let me write a pH, it's always lower than the vapour pressure of our pure solvent. So I write here P naught, right? So what is the P naught? That I just write as a symbol. So what is the meaning of the P naught? vapor pressure of the pure solvent. What is the PS? I write is here vapor pressure of the solution, right? So remember that vapor pressure of the solution is always lower than the vapor pressure of the pure solvent. Say for example, vapor pressure of the pure water. I write vapor pressure of the pure water. So in millimeter of the mercury, that is 760 millimeter, right? 760 millimeter of the IC. So when we mix with some amount of the solute, suppose I write water plus the solute aluminated sodium chloride, that is the sodium chloride solution. Sodium chloride aqueous solution, right? This is a solution. How much sodium chloride we add is another case, but when we add some amount of solute into the water, so the vapor pressure of the water, it's now become the solution. The vapor pressure of the aqueous solution is always lower than the vapor pressure of the pure water. That means the vapor pressure of this water, the vapor pressure of this solution is less than 760 millimeter. Don't forget our mercury level. So what we learn from the idea what I share with you, that okay, vapor pressure of the solution is always lower than the vapor pressure of the pure solvent. How much lowering? That is another case. Now here, that means the lowering of vapor pressure, that is the difference. What's the difference is vapor pressure of the pure solvent is always higher than the vapor pressure of the solution. So this lowering vapor pressure, let me write it that P is equal to P naught minus PA. So we remember that. If you know our solution, how much vapor pressure is lowering, right? So we can find out what is vapor pressure of pure solvent and what is the vapor pressure of the solution. So let me take a simple example here. I just remove this one. Let me just give it a simple example here. So vapor pressure of our solution. Vapor pressure of our solution here. So how much it's lowered? I write lowered by how much? See, I write 10%. How much percent is the vapor pressure of the solution is lower? 10%, right? So I just express in terms of the percentage. That means this lowering of vapor pressure, what will be the answer? That should be the 10, right? So now here, what I is scaling from the here. What I is just scaling here, the vapor pressure of the solution. Now here, the vapor pressure of our pure solvent is taken here. Vapor pressure of the pure solvent is taken here is the percentage, that is the 100, right? If you know the vapor pressure of the pure solvent, so as I took the percentage, now here the vapor pressure of the pure solvent is taken here 100. So how much is lowering vapor pressure of the solution? Lower by the 10%, that means 10, right? So what will be the vapor pressure of the solution? That means delta P is equal to P naught minus P, what should be the solution? So here how much that is 10, how much this is the 100, so minus PS. So what will be the PS? PS is equal to 100 minus 10, that is the 90. So this is the way how we can calculate it, right? But if you keep remember that it's always the vapor pressure of the solution is always lower than the vapor pressure of the pure solvent. Now here one more thing that we remember, that how much lowering of vapor pressure when we add some amount of the solute, right? So remember, lowering of vapor pressure is directly proportional to the amount of the solute. Let me write W solute, that is the amount of the solute, maybe in the gram, right? See, when you add more, so it will be more lowering. When you add less amount of the solute, that will be the less lowering. See, I read this one. I just wrote one line. This is the vapor pressure of our pure solvent. Suppose this is the water. What is the vapor pressure of the pure water? As I took the 760 millimeter, right? So now I add the 2K solute. One is I write one solute. I write here that is the sodium chloride. So how much sodium chloride? We have the two solutions. I write solution 1. In solution 1, how much sodium chloride we take here? 10 gram, right? Then in the solution 2, when I just prepared the solution 2, in that solution, how much sodium chloride we added? 20 gram. See, the amount of the sodium chloride is different in the two different solutions. In the first solution, 10 gram only, and in the second solution is also to 20 gram. But how much water I took it here? The amount of the water I took it here. This amount of the water in both the solution is same. That let me write 100 ml, 100 ml. Here also 100 ml in the body solution. So same quantity of the water, but the quantity of the solute is different. In solution 1, 10 gram. In solution 2 is 20 gram, right? So since the amount of the solute is different, so the lowering of the vapor pressure also be different. So which one should be more lowering, which one should be the less lowering? So as I write here, the lowering of vapor pressure is directly proportional to the amount of the solute we added. More solute we added, more lowering. So now here, which solution will be more lowering? See, this is the vapor pressure of the solution. Pure solvent, 760. Obviously, the vapor pressure of the solution should be less than 760. So, which should be the more lowering, which should be less lowering? So, I draw the simple graph here. Just I draw that. Right? This is the lowering. This is the lowering. Right? Here. So, here I just draw the two lines here. With two lowering. So, just let me mark it. The first law, this one, which solution will be related, and this one, which solution will be related, as we know that amount of the solute in our solution, solution 2, that is 20 gram, the amount of the solute in our solution 1 is 10 gram, so the amount of the solute in the solution 2 is more than the solution 1, therefore, so lowering of the vapor pressure of the solution 2 will be more lowering than the solution 1. That means this should be the solution 2 and this should be the solution 1. What will be this is the lowering of the vapor pressure, this is also lowering of the vapor pressure, but which one is more lowering? That should be the solution 2, because the amount of the solute we added here is more than the amount of the solute we added in the solution 1. Right. So this lowering of vapor pressure is the properties of the solution, right? This lowering of vapor pressure is also the one of the very important properties of our solution. As we mentioned that lowering of vapor pressure is always depends on the amount of the solute we added, right? Now here, this lowering vapor pressure, so we can express in terms of relative relation, relative form of our lowering. So relative lowering of vapor pressure of the solution, right? So here the relative lowering of vapor pressure of the solution, that is our colligative properties, right? So how do we write here? So this is the lowering vapor pressure divided by the vapor pressure of the pure solvent, that is what we call the relative lowering of vapor pressure. Now here the relative lowering vapor pressure is a colligative properties. Why this relative lowering vapor pressure is a colligative property? Now reason here. Here the relative lowering vapor pressure is always depends on the number 1 amount of the solute. This amount of the solute, right, we sometimes express in terms of the number of the moles of the solute, right? So this amount of the solute we also can express in terms of the mole fraction of the solute, right? And this amount of the solute we also express in concentration term. So what concentration term we can say here? Molarity, or it can be say the molarity. right? So these are the different expression of the amount of the solute here. So now here, when we explain about the colligative property is the what is the properties of the liquid, right? Which depends on number one, amount of the solutes added, number two, number of the moles of the solute present in the given amount of the solvent, or the mole fraction of the solute, or the molarity or molarity, right? But here the most important is just what the concentration term of the our solution. This colligative property is related, that is molarity, not molarity. Please keep it in mind here. So now here, how we express our colligative property, that means the relative lowering of vapor pressure in different mathematical expression. I just going to write here. See here, what is the most important mathematical expression here? What is this? This is the relative lowering of vapor pressure. What it does mean, that is the colligative property. Why this relative lowering vapor pressure is a colligative property? Because it depends on the mole fraction of the our solute. Right? Remember. So when we calculate the mole fraction of the solute, so suppose the solution is the binary mixture containing the two components, one is a solute, another is a solvent, right? So when we have a two components mixture, so how do we calculate the mole fraction of the solute? As we know that mole fraction of the solute is equal to number of the moles of the solute divided by number of the moles of the solute plus number of the moles of the solvent. So we do calculate the mole fraction of the solute here. So mole fraction of the solution is the what is the ratio of the number of the moles of the solute and total number of the moles of the components present in the solution here. But when we do the calculations, when we do calculation of the relative lowering vapor pressure, the solution should be the very dilute solution, not a concentrate one. So we can approach in the dilute solution or we can approach in the concentrate, but we prefer to calculate in the very dilute solution. For a very dilute solution, dilute solution means that in terms of the amount or number of the moles of the solute and the solvents present in our dilute solution, this number of the moles of the solute compared to the number of the moles of the solvent is very less compared to the number of the moles of the solvent. Therefore, this number of the moles of the solute can be neglected. So we can consider only the number of the moles of the solvent in our very dilute solution. Therefore, this X solute, that means mole fraction of solute. So for the dilute solution, so this mole fraction of the solute, we consider only the number of the moles of the solute divided by number of the moles of the solvent. Now here, this mole fraction of the solute, we can express the relative lowering of vapor pressure. So can also be depends on the number of the moles of the solute divided by number of the moles of the solvent. But here we only consider the solute. Remember, here we just calculate in terms of the mole fraction. Now here also we can relate it to the number of the moles of the solute. So here is the one of the our colligative property, mathematical expression. This is another mathematical expression, right? Then now, as we know the number of the moles, either solute or solvent, how do we calculate? One of the approach is the number of the moles we can calculate from the given mass of the any substance here. So if I consider the solute, so how do we calculate the number of the moles of the solute? So we can calculate the mass of the solute. So it divided by the what types of the solute is given. If we know that, we can find out the molecular or molar mass of the solute. Similarly, number of the moles of the solvent here also we can do. Here that is W solvent divided by M solvent. So we can put these two here, and solvent here and solvent here. So we can put it here, that is relative lowering of vapor pressure is the colligative property which depends on the mole fraction of the solute. We write this one, and it also depends on the number of the solute. We can express this one, and now here in the place of the N solute we can write W solute divided by M solute. What is the M solute? Molecular mass of the solute or molar mass of the our solute. Now here, see, this is the part of the N solute and divided by N solvent. So when we just write it here, so now I bring here, that is the M solvent divided by W solvent. As I mentioned before, so the relative lowering of vapor pressure is a colligative property which depends on number one mole fraction of the solute. Just we write this one. Okay, this colligative property is also depends on the number of the moles. It's already given here, right? And here this relative lowering vapor pressure is a colligative property which depends on the amount of the solute. So we express this equation, right? Okay. Then now from this equation, what are the parameters? See, this delta P we can write a P naught minus Ps divided by P naught. Now here this W solute is given here, this M solute is given, M solvent. No doubt M solvent, no doubt it will be given to you, and W solvent it will be given to you. The basic question it's normally asking, that is the mass of the solute, how much it should we use to get, okay, in order to lowering the solution. And from the lowering of the solution, from the given mass of the solute, what is the molecular mass of our solute? So here, this colligative property, one of the important thing is that this colligative property is the one which can calculate the molecular mass or molar mass of the solute. So this is the one of the approach how to we calculate the molecular or molar mass. Now here, so this expression we can convert it into the concentration term. What concentration term? We write it as here, W solute. It was written here in number of the solute divided by molecular mass of the solute or molar mass of the solute and multiplied by the W solvent. Now here, these three factors when we write it here. So amount of the solute divided by molecular mass of the solute, that is what we call the number of the moles of the solute. This is the number of the moles of the solute present in the given mass of the solvent. What was the concentration terms we call? That is the molarity. I write here N. Okay. So now here, this part is just related to the molarity. Therefore, relative lowering vapor pressure, right? Instead to write these things, so I write M. What is M? That is the molarity. What terms it remain here? This is the molecular or molar mass of the solvent. But when do we calculate this molarity? This weight of the solvent, it should be in the 1 kg. Remember. So here in the 1 kg, this 1 kg, and this is the molar mass. This molar mass is given in the grams per mole. So here is the kg, here is the gram. So in order to calculate in this equality unit, so I just write here 1000. So this is the our equation we can derive from the above equation. So here, so now here, what is this? This is the relative lowering of vapor pressure. What is this relative lowering vapor pressure? It's a colligative property. This colligative properties, in what concentration term it depends, that is the molarity, not molarity, not normality. Keep remember this one is very important. So here, in this case, what we can just remember, you here the molarity is given here. If you know the molarity, if you know the molarity, if you know the what type of solvent is given there, we can find out what is the relative lowering vapor pressure. So these are the mathematical expression for our relative lowering vapor pressure here. Next, okay, we have another colligative properties. What is the another colligative properties? Before I just pick up here, see, remember. So, vapor pressure, when we learn, so as I said before, vapor pressure is playing a very important role, okay, in order to find the another properties of the liquid, right? So, what is the another properties of the liquid is boiling point. Now, what do we mean by boiling points? You know boiling point is the temperature. What temperature? Here, in our case, so boiling points, we have two different pressure. Okay, one is the pressure that is the vapor pressure of the liquid, and another pressure is related to the external pressure, what should we call it, atmospheric pressure, right? So here we know the vapor pressures. You know the vapor pressure, it means the escaping tendency of the liquid, right? So that escaping tendency of the liquid is related to our atmospheric pressure. If our atmospheric pressure is the very less, so vapor can easily vaporize. That means liquid can be easily vaporized. That means our liquid itself is now very high vapor pressure. That means at the low atmospheric pressure, so liquids now it becomes high vapor pressure. At the high atmospheric pressure, right? So our liquid itself, it should be the very low vapor pressure. So you remember that. That means the conversion of our liquid into the vapor, that is what we call the boils, right? So any liquid what start boiling means, okay, the liquid that is converted into the our vapor phase. So for conversion of that liquid into the vapor phase, we have a certain temperature required, right? The temperature for such a conversion, that temperature what we call a boiling point. But that is our logic. But the real chemistry is, so we require the temperature in order to bring the equilibrium of our vapor pressure of the liquid and the atmospheric pressure. That types of the temperature what we require to bring our equilibrium state of our vapor pressure on our atmospheric pressure. That temperature what we call our boiling point of a liquid. Remember here. What is the relation between the vapor pressure and the boiling point? As I know, as you know that, okay, what is? So, lowering the vapor pressure means those liquid having low vapor pressure, that means difficult to vaporize, right? That means in order to vaporize that liquid, so we require more temperature. If we require more temperature to vaporize, that is the temperature which is converted from the liquid into the vapor. That is what we call boiling point. That means those liquid having the low vapor pressure, right? That liquid will have the high boiling point. That means more lowering the vapor pressure, it should be the high boiling point. Keep remember that, right? That means the vapor pressure of the solution is always lowering on addition of our solid, right? The lowering the vapor pressure, obviously the boiling point of our solution will be increased. Such increasing the increasing the boiling point of the solution. So we express in our chemistry language that is the elevation. elevation of the boiling point, right? So that means, okay, the lowering of vapor pressure of the solution is elevation of the boiling point of our solution. Keep remember that means, right? So what is the what is the relation between the lowering of vapor pressure and the increasing of vapor pressure, boiling point? So increasing means elevation. Elevation means just this is the elevation, right? Suppose if I consider this is the boiling point, so this boiling point is inclined up, right? So that means elevation. If I consider this is the vapor pressure, right? When we have the solution, so the vapor pressure of this solution is always lowering like this, right? More lowering, more elevation, right? Understand? So this elevation of the boiling point is also depends on the, as I said before, this elevation of the boiling point is also depends on the amount of the solute we added, because when we add the more amount of the solute, right, more lowering of vapor pressure. If the vapor pressure more lowering, the boiling point of the solution more elevated, right? And number two, this elevation of the boiling point also depends on the number of the moles of the solute as we expressed at the time of the vapor pressure, right? And here this elevation of the boiling point also we express in terms of the concentration. So what concentration term this elevation of the boiling point also related to, that is also molarity, right? So now here what do you mean by elevation of the boiling point? Here the elevation of the boiling point is also one of our colligative property. Why this elevation of boiling point is a colligative property? Because it depends on what, and so I just said here before, right? So now here this elevation of boiling point. Now let me here boiling point of our solution. Boiling point of our solution. Let me write here TH is always higher than boiling point of our pure solvent. Higher T0. That means TS is always higher than T0. That means boiling point of our solution. Boiling point of the solution is always higher than the boiling point of the pure solvent. So we have the difference, right? What is the difference between these two? Delta PV. That is the difference of the boiling point of the solution and the boiling point of the pure solid. This difference between two, that is what we call elevation on the boiling point. So this delta PV, that is what? Elevation on the boiling point. This elevation on the boiling point is always directly proportionate to the what concentration term, that is the molarity. What is the molarity? I write this small m. So we already define the molarity, right? So now when we converted, this is the mathematical equation, I just remove the proportionality sign. Now I write the constant. This is the kV. Now here, what is the kV here? This is the molar elevation constant, right? So this molar elevation constant also called ebullioscopic constant, right? I write here spelling ebullioscopic constant. This kV is the what we called molar elevation constant, or what? Ebullioscopic constant here. See here, this is the what we call elevation of the boiling point. What is the elevation of boiling point? Is the difference of the boiling point of the solution and the boiling point of the pure solvent, right? And this elevation of the boiling point is directly proportional to the one of the very important concentration term is molarity, not molarity, keep it remember, not normality, right? And now when we write in our mathematical expression, that is I write this constant. What is the kV? What is the kV? Molar elevation constant. This molar elevation constant, right? So the value of the kV is always depending on the nature of our solvent. Understand? I remind you, right? So this kV value is depending on the nature of our solvent. This kV is not dependent on this concentration. This kV is not dependent on this value. This kV is always depends on the nature of our what? Solvent, right? That means kV value is different in different solvent, right? Some of the solvents, this kV value is very high, and some of the solvent, this kV value is very low, right? So now, what is our importance of this kV value? So it's listed in our book. So some of the, see for example, see water. What is the kV value of the water? Yeah, 0.52, right? But the others, so we can have the benzene also, cyclohexane also, some are very common solvents are there. So those solvent having the high kV value, so high kV value. So if the kV value is very high, those solvent having the high kV value, that solvent is the better solvent in order to find the elevation and the boiling point, because this solvent does not interact with our solute with it. So the best solvent, what is our condition for the best solvent? Better solvent, I write better solvent. See, in order to determine, see here is the one constant we have it in our previous colligative property, in our relative lowering vapor pressure, there is no any such a constant value. But in our elevation and the boiling point, we have the one constant, that is our molar elevation constant of different solvent. Now here, so these different values of the kV, I mean different kV values of the different solvent. What's our solvent we use as the better solvent in order to determine the elevation and the boiling point? Here the basic chemistry is, remember that the solvent what we took it should not be interact with our solid we have, right? Should not be, right? No interaction, no chemical interaction. Solute remain with solute and solvent should remain as a solvent, right? No interaction, less chances to, less possibility to interact with the solute and solvent molecules. So those liquids, having the high kV value, that solvent, it means that very less chances to interact with the solid molecules. Therefore, that liquids, having the high kV value, we use as the better solvent in order to determine the delta kV. Not only delta kV, so here is the another aim. What is the aim? Molarity. As we know what is definition molarity, so that is we write W solute divided by M solute multiplied by W solvent. So now in this equation, what we normally do it here, that is the calculation of the molecular mass of the solute. So in our previous colligative property, relative lowering of vapor pressure, that also possible to calculate the molecular mass of the solute. From that equation we derived. Now here also elevation of boiling point is our colligative property which can determine the molecular mass of the solute here also. So now here, so which solvent can be used, can be the better solvent, in order to determine the elevation and the boiling point as well as the molecular mass of the solute here. That is the solvent having the high kV value. So amongst them, so it one of the solvents can be considered the benzene also high kV value compared to the water, and cyclohexane also very high kV value, okay, compared to the water and even nitrogen also, right? So amongst them, those liquid having the highest Kb value can be used as the better solvent. So in order to determine the delta Pv as well as the molecular mass of the solute. So these are some basic idea related. These are the important chemistry we should remember about our colligative properties. Okay, we have two more colligative properties there. So that remaining colligative property we can discuss in our next class. For today, let we learn this much. Okay, so you please remember and you please try to learn this, right? So if you interested, you can subscribe my YouTube platform and you can share with your friends and who are very interested to learn about my chemistry, know your chemistry. Thank you very much.